Hi, everyone. I don't want to disappoint you, but this paper is not about IoT or CPS systems, but I still have some correlation. It's a bit higher level. It's about bridging the gap between control flow integrity and attestation schemas. It's a joint work that has been done in the TSS lab, which is part of the Huawei Munich Research Center. So I would start by saying that remote attestation concepts have been well researched, and even different solutions have been applied in some industrial product scenarios to achieve both boot time and load time integrity guarantees. But once the software is up and running, it's always the question about what about the runtime state. And for this, I have this collection of pictures. I'm pretty sure many of you have seen one of these pictures. I'm not really, which talk about the dominance of memory corruption vulnerabilities in the wild. I'll not really stick to these pictures, but I'll just stick to a simple fact, which is really our software is really complex. It has so many bugs, and these bugs are really exploitable at runtime in different ways. And of course, the most major techniques are code injection attacks or code reuse attacks. But code injection attacks have been largely mitigated because of deployment of some defenses like data execution prevention. But code reuse attacks are still really a real concern. And in this presentation, I'll focus on control flow hijacking. But as a response, we have seen several runtime mitigation techniques. They have been even targeting different attack steps. Some of these techniques have been even deployed in some products. For example, we have ASLR. But of course, they managed to raise the bar for attackers, but they didn't really manage to block the attacks completely. But again, in my talk, I really focus on the techniques that have been specifically designed to mitigate control flow hijacking attacks. And here I talk about CFI and CFA, which control flow integrity and control flow attestation. So control flow integrity is just like a runtime enforcement schema that has been designed to restrict the execution or indirect branch instruction, just to adhere to some statically generated control flow graph. And it has been really extensively researched in the past 20 years or even more. And we have so many proposals that they are trying really to address the trade-off between different aspects like performance versus security and so on. But nevertheless, the common factor among all of them is that they are really operate at the local level. And this is by itself is good. I mean, from one hand, it's really allow for relatively easy deployment for CFI defenses, and the CFI did really a great job in blocking really many attacks. But on the other hand, the runtime integrity guarantees are not really in place when we have some gaps in the designs or implementations. And just to show this limitation, I'd really like to discuss it from two different perspectives. I mean, since the emergence of code reuse attacks and we have the seminal work on CFI, we started to see so many CFI proposals to address different aspects. But at the same time, we have been also seeing so many attacks that are trying really to overcome these solutions. And if we really try to look at the enabling elements of these attacks, we will find different factors. And these factors are really ranging from granularity issues to implementation and corner cases issues up to even what we consider nowadays is just a weak adversarial model in the time of microarchitectural attack. And we have seen, for example, in USENIX this year, just two papers, which are the last column talking about or bypassing even the modern defenses of CFI. But even in the ideal scenario, CFI itself is not really enough. As I mentioned, it does a really pretty good job in consumer devices like mobile phones. But in many other scenarios, for example, we have service providers in the cloud domain and core networks. They are really, they want really to have some extra more information about what's going on during runtime. Even enterprise customers, they always ask for verification solutions to make sure that they really try to reason about the runtime integrity of these solutions when they are really running. But of course, once we talk about insights, results, reports, they really need to be trusted somehow. That's why, unfortunately, existing CFI mechanisms can't really be extended to handle this external things because they have been designed actually to be stateless for performance reasons. They can't really give these extra informations to the outsiders. And this was one of the main reasons of handling or of proposing control flow attestation concept. And CFA as a concept is just a challenge response protocol that allows verifying the runtime integrity of the prover device by external party that is called verifier. And it, as a concept that has been emerged like 8 or 9 years ago, we have seen several techniques that are trying or just like to solve different challenges that just like around realizing it as a solution that could be applied in a product. And the way how it works, it just like the prover is always instructed just like to build authenticated log about like the executed control flow instructions. And these instructions would be offloaded at some point in time to the verifier for verifications. And normally this report or this log is always constructed using software instrumentation or even like customized hardware and sometimes a combination of them. But unfortunately, existing solutions, they have been really designed for embedded systems. They have been targeting just like simple embedded devices, and porting these solutions to the high-end system is not really going to be a good like solution or a good way, a good work around it, because like we will always have these runtime overhead and security concerns. But even like the few ones that have been targeting like complex software stacks, which are really like they are really like the most important ones, just like to handle the runtime integrity aspects of them because of like the larger attack surface. Even those ones that have been really trying to target like the complex software stacks, they are still far from being practical because of runtime overhead, but also they have been designed in isolation of the CFI mechanisms. And it always triggers this question about, can we activate two CFI and CF schemas on the same device at the same time? I do believe, or many of us maybe will believe, like this would be really like a huge overhead, and it's not going to be the case. And again, this would trigger another question, which is about, but CFI has a distinct feature and control flow attestation has another nice feature, and how to combine both, how to really achieve both features in just like one design. And this is the goal of CFA+. We just like try to take a first step, just like to bridge this gap. And simply like CFA+ is just like a control flow attestation mechanism with local remote detection, local detection capabilities. And we tried really to achieve this design and to make sure that we achieve really these capabilities in just like one design that could be really efficient, scalable, and at the same time practical to be applied maybe in some scenarios. And it does really depend on two main pillars. The first one is just like we apply some lightweight software instrumentation to make sure that we really try to monitor the execution state of our software, but we try to do some kind of implicit monitoring by just like dedicated some two general purpose registers that we call SR and RR, state register and reference register. And these registers are really used just like to encode or just like to maintain some really relevant execution aware information about like what's going on. And the second main pillar, which is we try to leverage like the landing pad instructions that are already available in the modern architectures nowadays. And in the ARM, they are called the branch target identification instructions or BTI instructions. And those landing pads, as you see from the picture, if you really insert the landing pads in some places, like the processor would enforce like the indirect branch instruction, just like to follow these landing pads. Otherwise, an exception would be triggered. And in terms of realization of these two pillars or positioning of these two pillars in our instrumentation, we identified the three code elements where we apply our instrumentation. And the first one, it's just we instrument like call instructions, and here we target all call instructions to non-leave functions. It's obvious like that we target like indirect call instructions because we need to track them, but also we track direct, we instrument direct call instructions because we want to track to return instructions like through them. And we also instrument like the entry and the exit points of each function to make sure that we always allow just like legitimate calls, or at least if we even like we just like have some like non-legitimate calls like bypass, at least we manage to detect them later. This is the overall all architecture of CFA+. It consists of three parts. We have the compiler tool chain. We have the prover side where we implement like an exception handling module that once it triggered, it does really just like do some jobs like logging some minimal data for our attestation reports, and also even anchor these results in the root of trust. And we have the verifier side. And just like quickly looking at each of these parts, in the instrumentation or in the extended compiler to the chain, like our instrumentation or the transformation that has been made by our plugin, it's just like try to do what I described, just like in terms of instrumentation. So for example, in case of having here our main function, just like invoking a function called the check privilege, Of course, at the beginning, we initialize our two dedicated registers to some custom values, which here it's 0. And then we can see like the call instruction here, it's just like surrounded by our instrumentation. And what we do is just we generate a unique ID for each call instruction, and we try to encode our state register before the call, and we decode it after the call. But directly after the call also, as you can see, we insert just like a landing pad for return instruction to make sure that the return always just like go to this place. And even if just like we have some corruption in some return addresses and the return would just like target a different landing pad, of course, the decoding steps would be just like done with a different ID, and this means that we will have consistency with the SR, which would be eventually detected by our verifier. And in the calling side, I mean, here, this is just like a direct call. It's simple. What we do here is just like we also try to encode or even like assign and verify the return addresses that are pushed to the stack and popped from it. But we do provide also like further details in the paper about like how it would be really the case for really like some functions that are potentially like that have their addresses taken, and they are really potential for indirect calls. Also, we really discuss in the paper about how we could potentially even integrate this solution with what we have it as what we call it Pointer Authentication code, which is another feature that is available in the ARM architecture. I know that I'm abstracting over so many technical details here, just like for the interest of time, but I would be happy to answer questions after this presentation, or even I would just like refer to the paper to have a look at this. And for the prover side, or for the runtime side on the prover device, what we do is just like, as I mentioned, we once the software is just like up and running, we just like have this implicit monitoring concept that like the software would just like keep executing, and our registers would just like keep updated because of these encoding, decoding schemas. I'll not really comment here about on the reference register, but it just like I would like to mention that it's really used for speeding up the detection of corruption that could be caused by external libraries. But also I would like to mention that our instrumentation, it's really like fine grained at the instruction level. So even if we have two calls from the same instructions and we just like try to return to a different location, this would be either immediately detected depending on the case, on the function itself, or it could just like cause consistencies in SR that would really even later detected by our verifier service. And the main component of our attestation report is just like these three register values, which is our state register, our reference registers, and also the program counter. And in terms of verification, like we try to implement like a very like efficient and scalable verifier module. We will just like utilize the SR value plus our labeled control flow graph that we generated during compile time, just like to extract all the paths that have been that would contain just like the reported SR value. And then we just like reason about the consistency using the two different reported values, which is the reference register and the program counter registers. And here I would just like even like show, maybe it's not really clear, but I just like show even a screenshot from one of our like internal demos where even you could just like show that the verification process itself, it could be pretty quick even for fairly complex software scenarios. It could be just like even less than 1 second. And once we have something really verified, we could even report about like the exact path that has been already executed when we asked for the attestation request. In terms of concluding remarks, we have implemented CFA Plus like completely, like even adhering to some TCG standards. I don't really, I try to skip over like so many implementation details, and even we have extensive evaluation results like reported in the paper. But what I would really like to mention in terms of evaluation results here is that CFA Plus is really several order of magnitudes faster than comparable CFA and CFI schemas, because it does really like implement like this. First of all, it depends on this implicit monitoring concept, and second, it just like leverage some really these recent instructions. So the overhead in general is just like, in average, is just like less than 3% overhead. And of course, we pay some extra time in terms of memory footprint, but we discuss also in the paper some optimizations. But nevertheless, of course, it's not really a one-size-fits-all solution. We also discuss in the paper about some limitations. It might not really fit all software scenarios. And of course, like there is always room for innovation and improvements, and even for proposing like better solutions. And if there is just like a takeaway message, just like to take it from this one, we believe that hybrid techniques with even both local and remote detection capabilities are really needed, and they are really essential. And there is really a room for proposing even maybe like better techniques, just like to handle different use cases. Thank you.